Hi everyone, my name is Haibin. I've been working at Amazon for a little bit more than a year. I mainly work on the MXNet backend engine. In today's talk, I'm going to introduce you the Sparse Tensor feature in MXNet, specifically what kind of data that is sparse, and also what kind of performance optimization you can get in terms of speed, memory, and communication, especially if you're working on large-scale recommender system or natural language processing applications. So let's get started. There are two types of tensor that we'll consider in MXNet. One is sparse data, another is sparse gradient. Let me give you an example. So let's say you're given a dataset with users' ratings on movies. So you can potentially get millions of movies and also millions of users. But you will notice that for a user, typically he only look at a few hundred movies. And if you represent matrix in dense format, most of the entries in matrix are zeros. So if you represent it in the dense format, it wastes a lot of memory. And if you do a simple multiplication on this matrix, it wastes a lot of computation on just computing the zeros. That is not what we want. Instead, we can take advantage of the sparsity in the dataset. Basically, instead of storing all the entries in the matrix, we can store only the non-zero entries with their values and indices. This way, we save a lot of memory when we're storing this matrix, and also while doing computation or communication, we only need to care about those non-zero values. So the example I gave you is a recommender system example. This is a huge matrix with a few non-zero entries. And you can find similar pattern when you're working on social networks, where you have the friendship relationship. There are a billion users, but for each user, he's only with friends with 1,000 or so. In MXNet, you can use the CSR format to represent this kind of sparse matrix. Now, another kind of tensor that is sparse is the gradient. Let me give you an example in the NLP domain. So let's say you want to train a language model. So the task is basically you're given the words in history, and you want to predict the next word based on history. What you typically do is you take the input token X, you feed it into an embedding layer so you get a vectorized representation of the word, and then you feed it into the RN layers to capture the temporal dynamics of the sentence. After that, the output of the RN layers is fed into the fully connected layer, followed by a softmax layer at the end to compute the probability of each word in the vocabulary. One thing to notice is that the embedding layer is huge. You can represent the embedding layer this way. For each word, there's a vector associated with this. But if you do the training in a mini batch, let's say in this mini batch you have the sentence, the fox jumps over the lazy dog, you will only have non-zero gradients for the words that appear in the mini batch. For other words that don't appear in the mini batch, they have exactly zero gradients. So we can store this matrix in a much better way. Specifically, we can just store the word IDs for the words that appeared, and also the values for the non-zero entries. And in MXNet, you can store this in a row sparse format, where we just basically store the row IDs and the non-zero data. So this is the format for a matrix where each row is either all non-zeros or complete zeros. In case you haven't used MXNet before, I'm gonna show you some sample code to see how you can load a sparse matrix and perform operation on it. So here's an example. Here I'm importing SciPy and MXNet, and first generate a SciPy random matrix, 2x3 matrix with some density and data type, and then you can load it, and then you can turn it to an MXNet CSR matrix by calling the mx.ndarray.sparse.csr matrix API, and here you can also provide context equals to CPU or GPU to load the data. So now we have a sparse matrix in MXNet. Let's do some sparse operations on it. Here is an example. So first I create a sparse vector W. It's a vector of length 3. Then I just perform sparse matrix multiplication by calling the sparse.dot API. And then you can see this is the result. In case you are curious how fast it is, here's some benchmark result. So we did some benchmark on the KDD dataset. This is a dataset with 20 million features, and for each example there are only a few non-zeros. You can see that comparing the sparse multiplication and dense multiplication, we get around 500x speed up, and also it saves tons of memory for this extremely sparse dataset. So far we've seen the speed and memory advantage if you use a sparse feature for your sparse dataset. Another thing I'm going to cover is the distributed training part for this kind of model. So if you have a high-dimensional sparse dataset, usually we'll have an extremely large model. Here's what you typically do when you do a distributed training. You have a parameter server which keeps a copy of the model and keep it up to date. You have multiple workers. Each worker keeps a copy of the model and a subset of the data. Typically, the workflow is like the worker will pull the most recent parameters from the server. The worker will perform forward computation to evaluate the loss and a backward propagation to get the gradient. Worker will push the gradient to the servers. When server collects all the gradients from the other workers, it will aggregate the gradient and perform the update. But what happens if your data is sparse? But if your data is high-dimensional and sparse, you don't have to do this. If you train a language model with a few thousand words in each mini-batch, then the worker actually doesn't have to get all the parameters from the parameter server. Instead, you can look at the data, figure out, these are the 1,000 words that I need in this mini-batch. Then then the worker can correspondingly just pull a subset of parameters only for this 1,000 words instead of pulling, the total million words. In this way, the worker only pull a very small subset of data instead of transferring like 1 gigabyte of data across the network. You can end up only transferring only a few hundred megabytes. And with this subset of the model, the worker has sufficient information to perform. So the worker will perform forward and backward computation and push the sparse gradient to the server, which also saves a lot of memory. Here's some benchmark results for the language model application I just mentioned. Here the experiment is done on the Google Billion Words datasets. This is done on the 4 K80 GPUs. As you can see, the baseline is the performance compared to a single GPU, and the speed up is basically the scalability compared to a single GPU case. As you can see, the scalability is quite good because we did all this kind of optimization to reduce the communication and computation overhead. In case you are interested in learning this feature, here are the QR codes for the examples and tutorials for this feature. and hopefully you'll find it useful. Thanks.